criteria of the day. And right now, I need those of you online to confirm if you're seeing multiple linear regression. Can somebody confirm that online? Okay, thank you so much for confirming that. Okay, this is going to be the beginning of chapter 3. Okay, we want to start a new chapter now. All what we've done all the way to dummy regression, they are all simple linear regression model. Why are they simple linear? Because the numbers of independent is 1. But right now, we're going into a situation where the number of independent is going to be more than 1. Okay? Now, I want to welcome you to multiple linear regression. The word multiple, okay, depicts the numbers of independent variable we're going to have will be more than 1. Does that make sense? That's what it means. Okay, now in the outline, I'm going to walk you through what we call polynomial regression. And I'm also going to walk you through how to add more explanatory variable to a model. Okay, I remember what I work on in one of my capstone projects in college. What I did in Africa, look at the effect of exchange rates, inflation rates, and consumer price index on the gross domestic product of Nigeria. That was what I work on, which means I actually have to apply the multiple linear regression because, of course, I got more than 1 explanatory variables. Okay, now I need you to pay attention now. But let me tell you this. At times, when we want to characterize relationship between variables, we normally find ourselves at a crossroad on what kind of variable do I need to include in my model. But let me first start with this example. Okay, of course, I've walked you through a data set. Like, take a look at this now. We basically want to study relationship between daughter height and the mother's height. Oh, if I know what are the variables that will help us to predict the height of a daughter? Okay, and somebody can say, okay, why can't you use the height of the mother? Because the daughter is coming from the mother, right? When you take a look at that, of course, we're going to fit simple linear regression to that, where the model is going to be what I'm displaying, what you've done before. And that is the arrow code, of course. You've done all of that before. In the arrow code, at times, if you take a look at the first code, there's going to be 1 plus, right? If you look at the other one, there's no 1. It doesn't matter. You may put 1, you may not put 1. Where you don't plug in 1, arrow is assuming that you have an intercept in your model, because 1 is indicating intercept. Okay, is the coefficient of the intercept. Okay, so I first wanted to understand what we mean by predictors and regressors. In this model now, where we have a daughter height and a mother height, we got 2 regressors, but 1 predictor. What are the regressors? The regressors will be the coefficient of the beta naught and the beta 1. What is the coefficient of beta naught? 1. What is the coefficient of the beta 1? In this case, it's going to be x, which is representing the mother's height. So regressors is more than predictor. Regressors is predictor that the numbers of regressors is going to be numbers of predictor plus 1. What is that 1? The intercept. Does that make sense? That's what I mean. Okay, now, do you know that if I want to predict the daughter height, I may have 3 competing models in my mind. The very first model is model 1, saying the only, I think what is relevant to predicting the daughter height is the mother's height. That is what model 1 is telling me. If you take a look at model 2 is trying to say, okay, you need to add more variable, make it a multiple linear, and you also need the further height. Model 1 is a simple linear regression. Model 2 is a multiple linear regression. Let me tell you this. A model 2, how do we know which model is going to do the job? Is it a simple model or a complicated model? Of course, we actually have a way to figure that out. Okay, I'm going to show you all of that. And take a look at model 3. Model 3 is trying to say, okay, you know what? We only need model height if you want to make a prediction of the daughter height. But except that, we're also going to incorporate quadratic effect of the mother's height. Does that make sense to you? Take a look at the model 1, model 2, model 3. These are candidate model. Okay, at the end of the day, one model would be the most appropriate one. Because in statistical analysis, we basically want to figure out among the competing models, which one actually work great. Does that make sense? Okay. Now do you understand all the three models now? What we're considering? Now, I may ask you a question. If you take a look at what I wrote, linear regression with more than two regressors. Linear regression has two regressors, one predator, two regressors. The two regressors is going to be 1 and x, intercept, and the coefficient of the slope. Okay, now in the model 1, the number of predator or the number of explanatory variable is 1 because you have more than height, right? What is the numbers of regressors? 2. Take notes. For model 2, the numbers of explanatory variables is now 2 because you have the mother height and the father height. But what is the numbers of regressors? 3. Okay, 3. Don't forget. Now take a look at model 3. Can somebody tell me for extra credits? How many predator do we have in model 3? And how many regressors? Can somebody tell me? Model 3. Whether in person or online. Those of you online, can you hear me? Those of you online, you can also get an extra credit that you can use towards your assignment, midterm, and so on like that. The question I'm asking now in module 3, how many explanatory variables do we have and how many regressors do we have, whether in person or online? Can somebody tell me? Okay. Okay, 1 predator, 3 regressors. That is a very perfect answer. 1 predator in the sense that we're still talking about mother's height, right? But 3 regressors because we have 1 x and s squared. That is 1 mother height squared. Let me tell you, in module 3, there's only 1 predator, except that we have both linear effects and the nonlinear effects. The nonlinear effect is a quadratic term. Good job. Send me a message for extra credit. Okay, now what I'm going into right now, there's a reason why we do what we do. We don't just do what we do, right? So what is the reason? Why is it that at times we're not satisfied with using only 1 predator in a model, 1 explanatory variable in a model? Why do I need to add more regressors? There are 2 reasons, but I'll first give you the major reason why we need to add more regressors in a model. The major reason is we actually want a model with a better fit. We want to improve the quality of our model. How are you actually going to know if the quality of our model has been improved upon? Then the model will have a larger house square. You know what I mean by house square, right? You know, I've walked you through that. R square is the coefficient of determination. Okay, the coefficient of determination is going to tell you how much of the percentage variation in the dependent variable, okay, the model will explain. If the model explain more, right, then the quality of the model okay, is attained. That's what we mean. Okay, we add more regressors just to to have a kind of improvement on the quality of the model. Okay, now when you are adding, we do that in two ways. At times we could go polynomial. At times we could just be adding. Now when we go polynomial, okay, adding regressors but not explanatory variables. Why do we need to do that? Like when you take a look at model 3, okay, if you look at model 3, I'm not adding new regressors. I'm not adding new explanatory variable, but I'm only incorporating, the quadratic effect of model height. Why am I doing that? Okay, so why am I doing that? Because of the fact that the relationship between the dependents and the mother's height may not be linear. Does that make sense? That is why we're adding the quadratic effect. Maybe by the time you draw the scatter plot, right? You draw the scatter plot and you realize there's a violations of linearity. If there's a violations of linearity, and maybe probably what you see is looking like a curve, right? And that was the reason why you actually incorporating the quadratic effect. Does that make sense now? That's why you're incorporating that. Okay, so that is the reason now. Reason because the response variable, when I say response variable, I mean the dependent variable y, okay, may not be linearly related to that explanatory variable. And that is why I'm actually going to consider the idea of incorporating, quadratic effect or cubic effect, generally speaking, considering polynomial regression. Now, I just gave you a reason for applying polynomial regression now. Now, what is the reason for adding explanatory variable? Like somebody more explanatory variable. Somebody may want to ask model 2. Why is it that I'm not okay with just mother height to predict a daughter height? Why do I need to add a father's height? That is what we mean. Okay. Now, the reason here is that the response variable may be related to more than one explanatory variable. Okay. In a real life practical situation, okay, hardly can one find a situation where it is only one variable that will be explaining. You are likely going to have more than one variable. And that's why simple linear regression is not that appropriate. In a real life practical situation, I told you what I work on in my capstone project in college, where I look at, I was trying to identify some economic indicators of the GDP for Nigeria. And I come across a consumer price index. I was not satisfied with only using consumer price index. I also consider inflation rate. I also consider the employment or the unemployment rate. Okay, does that make sense to you now? Okay, I'm going to walk you through an example right now. Let's go into an example right now. Okay, we're trying to model the salary from years of experience for professional workers. And of course, if you want to start investigating, if you want to characterize a relationship between two variables, right now we're focusing when we actually want to look at the effect of experience on the salary of professional workers. If we want to start, of course, we know we're going to generate a scatter plot, right? Now, this scatter plot is actually telling a story. What is it telling us? It's trying to tell us using a linear relationship will not do the job. What are you seeing? You are seeing a curve, right? That's a curve. Okay, and that is the reason why a good start, if you really want to, when you try to characterize relationship between variable, before you specify your model, why can't you generate a scatter plot? Because the scatter plot will give you the sense of what the nature of the variable, the nature of the model basically going to specify. Now, if somebody now end up, fitting that, where it just uses a straight line, salary equal, the intercept is 48.5 and experience is 0.9, that is basically going to mislead. because a straight line relationship is not appropriate for this scenario. As you can see in this scatter plot. And that was why I said variation of linearity assumption. The simple linear regression model cannot capture the curvature in the data, and that is the reason why we need to incorporate a quadratic effect. We don't just do that. We don't just incorporate quadratic effect. There is something that you're going to see. We don't do what we do. There's a reason why we do what we do. Does that make sense? We don't just do what we do. Now, we now try to incorporate, take a look at that now. Salary equal beta naught plus beta 1 experience plus beta 2 experience squared. Why am I incorporating the quadratic effect of experience? Because I believe that may adequately capture the curvature in the relationship. Okay? And that was why I said adding the regressor quadratic term, right, helps the model capture the curvature in the data. What we're actually looking for, when we're trying to model, when we're trying to characterize relationship, we actually, if the relationship is linear model should be used. If a relationship is not linear, then if it's not linear, then don't use linear model. We want us to, don't forget, we actually want to capture reality, right, with a model. Okay. Now, if this is this is reality, and this guy is a model, okay, before we can actually capture reality, okay, then there must be an agreement between the model and reality. If reality is linear, use a model that is linear. If reality is not linear, use a model that is not linear. Does that make sense now? Otherwise, there's going to be violation, and you can no longer trust whatever that comes from your model. Now, the question now, how do we fit polynomial regression in R? I just supply you a code now. Take a look at that. You're just going to write salary on, you may decide to put one or not, that's no problem. But when you write experience, when you write your independent variable, before you're going to write experience squared, you need to put an indicator high. If you don't put an indicator high and you run it, the result is just going to look like that of a linear regression output. So make sure you put an indicator high. Now, right now, this is the result. This is the output. In the output now, you can see we now have more than two slopes, right? There's going to be a slope for experience, and there's going to be a slope for experience squared. Can you see that, right? That's what you see now. And if I want to know how significant is a quadratic term, I'm going to look at the p-value associated with the experience squared. What is that p-value? That p-value is less than 0.05, which means significant, which means we actually need to incorporate quadratic term. Does that make sense to you now? Okay, so take a look at all of that. And you know what? If you don't, like I said, if you don't put indicator I, it's just going to give you the result for linear regression. This is the result for linear regression, right? Now, there's something I want you to pay attention to now. What is the R square here? Can somebody tell me? What is the R square here? Here, what is the R square? What is the value of the R square? If you want to know that, you look at the multiple R square. That is 0.6754, right? Which means that when you fit a linear regression to the relationship, okay, the model will only explain 67.54%. But when you fit a polynomial, look at that. When you fit a polynomial, what happened to your multiple R square? Oh my God, your multiple R square are significantly increased. You see that? Your multiple R square has gone to 0.9247. Can you see that? It's 0.9247, the multiple R squared, for those of you online. So which means when you use an adequate model, okay, for a given situation, of course, your R square, the quality of your model can actually be attained. Okay. Now, how do you write down the fitted model? from that given scenario, you write down the fitted model, how much of the variation in salary is explained. Anytime they ask you that question, how much in the variation in salary is explained, you need to give them the values of the multiple r squared. Okay, you're going to multiply that by 100. How much of the variation out of 100%? It means out of 100% variation in salary, okay, experience explain 92.47%. Take a look at that. That's a great one. Okay. Now for the fitted model, you're just going to write a model. Let me see. I think the model is let me see if okay. So do you see the model? Salary cap equal, you write the intercept, you write the slope and the experience, then the slope for the experience squared. Does that make sense? So that's exactly what we mean. Okay. Now the next thing now is how can we interpret when you actually fit a model, whether polynomial regression model or whatever, you need to interpret. Okay. Now the average salary will be what? Will be 34.7 for workers with no experience. What is the meaning of no experience? Experience equal to zero. That's what we mean by no experience. When you plug in zero into experience in the fitted model, what does that give you? That will give you 34.7, right? Being the intercept. Now, how do we interpret the slope for experience and experience squared? Now, I said in polynomial regression, usually it is not meaningful to interpret the slopes in the contents. Okay, please take note of that. We don't, the polynomial regression, but there's something we can do if we want to interpret the slope, which is still going to do in this class. But for now, take it like that. Now, I quickly want to go to multiple linear regression. Okay, take a look at this. I actually want to predict the price. I'm looking for factors that will enable us to predict the price, of food in an Italian restaurant in New York City. And I'm considering there are three. Well, I got variable like price, food, which is a customer rating of the food out of 30, decoration rating out of 30. Now I'm considering three models. Model A, okay. I'm only considering variable food as a factor to predict the price. In model B, I'm only focusing on decoration, and in model C, I'm considering multiple linear regression, where I'm actually using the both food decorating and the other one. Now let's take a look at this. When I do a scatter plot, and for the price versus food, the R square is 0.39. That's a poor one, right? That one is trying to tell you using food. Okay, ready? Okay, that's only explain 39% variation in the price. That's a poor one, right? When I use decoration, a little improvement, okay, the R square moved from 0.39 to 0.52, which is good, right? Then another thing is, can we also improve upon this? Like, why can't we just combine the two, like the two variables in the model? Okay. Now, when you want to run linear regression in R, this is the code. Price, you may decide not to put one. Food plus decoration. Does that make sense? Okay. Even if you have so many variables, you're actually going to add them up. Okay. Now, this is the result. Now, what is the R square here? The R square is 0.6167, which was higher than any of these. You see that now? There have been an improvement. That is what it means. Okay. So take a look at that. Now, they can ask you to write down the model. If you want to write down the model, it's going to be the combination of the estimates. Then how much of the variation in the price is explained by model C. Don't forget the model C has food decoration. Has food rating and decoration rating. Okay. And of course, out of 100% variation in price, okay, that actually explain 61.67%. Okay. Now, how do we write the fitted model? This is a fitted model where you're going to have the price cap equal that plus 1.65 food plus 1.88 decoration. Okay, now when we have this guy now, how can we interpret here? Okay, Unlike in the polynomial regression, where interpreting the slope may not make sense, but interpreting slope will make sense in multiple linear regression. Now, I said technical interpretation now, when the full rating and the decorating rating are dash, the price of the dinner will be that. That will be when they are zero. Okay? The full rating is zero, the decoration rating is zero, the price of the dinner is that. But let me tell you this, that doesn't really make sense. Interpretation does not make sense at times when you are interpreting, but we need it in our model. Because how can you say the price of the dinner is negative? Like people coming from for dinner, you are even giving them, they buy food from you, and you're also giving them money. Does that really make sense, right? You sell food to someone, and you are the one giving them money. Okay, so that doesn't make sense. Now, take a look at this. How do we now interpret slope? Okay, we basically uh, going to, excuse me, we're basically going to interpret slope based on on food, the slope for food and the slope for decoration. Please look at the way we're going to interpret. If I want to interpret the slope for food, what is the slope for food? 1.65. I have to mention in my interpretation that I'm keeping decoration at constant. If I want to interpret the slope for decoration, I have to mention in my interpretation that I'm keeping food at constant. So take a look at this. Okay, that's when food rating increases by one, the price of the dinner increases by $1.65 on average. What is missing there is after adjusting or keeping decoration at constant. That is what is missing. Okay, keeping decoration at constant or adjusting for decoration. That is what we mean. Okay, so take a look at that. So when you take a look at the interpretation, there is going to be different from a situation where you only consider food alone. When you consider food alone, then it means you are not keeping any other variable at constant. They're basically going to have two different interpretations. So that is exactly what we mean. Now, you're going to do the same thing to decoration, the slope of decoration. In the slope of decoration, what is missing is after keeping food at constant. Okay? When the decoration rating increases by one, the price of the dinner increases by $1.88. Okay? And we also consider a situation where you did not adjust for the effect of food. Okay? So take a look at that. Okay. I think that's just the summary of what I've done today. Like what I've walked you through today is introducing you to a situation where you're going to have more than one independent variable, and more than one independent variable. You could have a polynomial regression. You could have adding more explanatory variable into your model. I think I've shown you how to estimate that, and I've shown you how to interpret the slopes and the intercept when you are working with the polynomial when you add in more variable into your model. Like I said, when you want to interpret the slope in a multiple linear regression, okay, when you are interpreting a slope associated with an explanatory variable, you need to mention that you are keeping every other explanatory variable at constant. For instance, apart from food, you only have decoration. In another multiple linear regression, there could be so many independent variables. If I'm interpreting the slope for one, I have to say after keeping other independent variable at constant, I have to mention that. Okay, so this is where I'm actually going to stop today. I hope you enjoy today's I hope you enjoyed today's lecture.
Real quick, Professor.
Yeah, go ahead.
About the practice problems on Canvas, where will they be located?
Oh, okay. Actually, there's a kind of communication gap between me and my TA right now, and I think I'm actually going to. I want to apologize for that. I'm going to do that myself. If I realize that your assignment has not been graded, and I think I've sent a last minute message to my TA. If it doesn't respond, then I'm going to grade assignment today myself. But I cannot guarantee you today you actually going to see the practice question uploaded on Canvas. Have I answered your
Perfect.
question?
Thank you so much.
You're welcome. Okay, any other question before I go? Okay,
Nope.
make sure you stay safe and have a lovely day. Bye for